So this signal, the height is proportional to the value of r. And this is an example of r equals to 0.01. And the current limit is r less than 0.07. LiteBIRD expectation will be like this. So the full success of LiteBIRD is to go down to 1 times 10 to the minus 3 if you talk about the error on R, which is like almost 100 times better than the current situation, and covering all low L region from 2 to 200. So this is the single most important purpose of this LiteBIRD Satellite proposal. And let me talk a little bit more about the cosmology parameter R. I said the first thing already, and so the R is proportional to the energy potential of the inflaton, V that I talked about already. And expected energy potential is around the scale of ground unification, as I already said. Measurement of B mode is just one of the most important topics in cosmology and particle physics, because you have a chance to really touch on the ground unification scale of physics. And current experimental limit is weak, so order of magnitude improvement required. And so that's a full success of LiteBIRD, I already said. Let me just skip all these detailed remarks. If you combine LiteBIRD measurement with others, you have a chance to even improve this error on R. Actually, here I'm not mentioning, but yeah, photo removal with low frequency survey. What I'm talking about here is that very low frequency that LiteBIRD will not cover can be provided by a ground-based experiment. Actually, the Quixote experiment is one good example. So probably I should add that to here. And so by, so there you can even think about upgrade of Quixote, and then some joint studies might all be very unique and useful. Okay, so that's about the motivation and science. Let me just briefly introduce the system. We plan to use this JAXA's new H3 rocket, which is capable of launching like a 3.5 ton, closer to 4 tons to Lagrangian point. So, and this is a satellite drawing, some satellite drawings. If you look at the envelope of H3, a LiteBIRD can be put in like this comfortably. It's not that large compared with other big missions. And so this is an overview of the LiteBIRD satellite. I'm going to go into some more detail, but before saying that, let me talk about the scan strategy. We plan to go to the Lagrangian point L2. That's same as Planck, but scan strategy is rather different. It's optimized for polarization measurements. So you can think of something similar to the spinning top with some precision. So here's the sun, here's the anti-sun axis. This is a deep space, and we have introduced these two angles. One is alpha. This is the angle between the satellite spin axis and the anti-sun axis. We chose 45 degrees. And the second angle, that's the angle between the spin axis and the boresight angle, which is 90 degrees in our case. And then spin rate is around 0.1 RPM, and this precession time is somewhere in between 90 minutes to 1 day. If you do that in sky, you expect to have this sort of trajectory. This is actually, in case we chose 91 minutes precession time. in 91 minutes, you will write this pattern on the sky. And in one day, you will cover this disk space. The nice thing is, just within one day, you really cover a wide part of the sky. So that's strategy. And then we eventually, our anti-sun axis just rotates. So eventually, in 1 week, this disk shifts a little bit. And in 1 month, shifts more. And then in 6 months, you see that basically you can cover the entire sky. But still, you have some non-uniformity. But in 1 year, you become you gain pretty uniform heat distribution on the sky. And you send that data to the JAXA's new ground station, which should be operational in a few years. And this is good enough for S-band and X-band as well. So we'll have a larger data link capability than now. So, and here's the LiteBIRD main specifications. I'm going to touch on more on the frequency coverage and some more technology, key technologies. Just briefly, we're going to cover the frequencies from 34 gigahertz to 448 gigahertz. So this is so wideband. So we plan to introduce 2 telescopes, low frequency telescope and high frequency telescope, or LFT and HFT. Then we're going to achieve this 3 microkelvin arc minute sensitivity, and we assume to have 3 years observation, and angular resolution should be better than 70 arc minute at any frequency. And we have a large field of view, and we have a cryogenic system to cool down the mirrors and also detectors. So now, if you talk about the products, here's the product tree and a little bit about international collaboration. So we'll have a service module which will be made by JAXA, and the payload module, high frequency telescope and low frequency telescope. And high frequency telescope will come from this here. It says ESA, but more correctly, it's from a European consortium. And then low frequency telescope is coming from JAXA, and we'll plan to use transition edge sensor bolometers, superconducting detectors, and these are coming from NASA. Okay, and cryo system, passive cooling chain and active cooling chain come from JAXA, whereas the sub-Kelvin cooling system is coming from European consortium. Okay, so that's the, and the data acquisition comes from Canadian Space Agency. That's a baseline idea. Let me a little bit talk about payload module. Low frequency telescope will be like this. The cross-dragon reflective mirrors like this. And on the most high side, we'll have a continuously rotating half-wave plate system for polarization modulation. So, and we have this TS bolometer focal plane array cooled down to 0.1 Kelvin. Here's the expected focal plane configuration and expected sensitivity. Probably, this is for professional use. I'm not going into detail. But one important fact, one important reason to introduce these many, 15 bands, is to mitigate foreground contamination. We want to observe cosmic microwave background, but foregrounds are anything else created after the CMB was generated. Well, this is also another professional, the detailed slide for experts. But what I want to say is that we have a team of world experts on foreground removal business, and we have a pretty good prospect, as written here, to achieve full success. So this study is still ongoing, But we are becoming more confident that the design we have right now will be adequate to really come to the full success. Now, a little bit about detector from US. We plan to use this wideband antenna using a lithography technique, CSIC antenna, which accepts really broadband light CMB photons. And in this case, we have two bands, 90 gigahertz and 150 gigahertz, in use for the polar bear experiment in Atacama. So for each frequency, you need two TS barometers for two polarization states. So that's why you see 4 detectors here. And this detector is coupled with lenslet like this. So that's a basic idea of the sensors we plan to introduce. And this is some more technical activities in Japan. Let me just focus on polarization modulator, which is an interesting one. So we plan to put this polarization modulator at the most sky side. And what it does is, it's basically a birefringent material, typically sapphire, and it's rotating. What happens is that when you have incoming polarization light, it's reflected by this, it's flipped with respect to the birefringent axis. And if you rotate the birefringent plate, you have this sort of rotation with a speed of 4 times the rotation frequency. And what you can do with that is, then the polarization is modulated, up-converted in your frequency. And once you demodulate that polarization signal, then you are free for whatever 1/f noise. So that's the idea. And here is one demonstration of rotation mechanism we are developing. This is using a superconducting magnet, and then so that's why you see this liquid nitrogen. It's very stable. It's very stiff, and then it has no, mechanical conflict or friction. So it has a long lifetime. And the cooling system is something JAXA is good at. For 1.8K and 4K, we plan to use JAXA's cooling system. And for the sub-Kelvin cooling system, we right now assume that that's coming from France, either ADR or dilution free. And we also have this new mirror design for LFT. Probably that's too much detail. And let me just very briefly talk about the project status. JAXA's evaluation is summarized here. In the JAXA roadmap, probing inflation from B mode is listed as one of top scientific objectives. So JAXA gotta do that in some way. And JAXA prefers focused missions for strategic large mission program. LiteBIRD is exactly a focused mission, so it perfectly fits this idea. So the current status is summarized by Toru Yamada, who is one of the management persons at ISS JAXA. LiteBIRD is a serious candidate for the strategic L+ slot in middle 2020s. And the final down selection for that slot is gonna take place hopefully by the end of this year. Details should be announced by JAXA, which we are waiting for. The current stage, phase A for concept development, will be ended in August this year. So this is a roadmap. So what we're talking about is this slot around 2026 or 7, and this one is LiteBIRD or solar power cell, and the final down selection will be made between two. And after that, Spica is supposed to be take this another strategic L class slot around 2030. And as some of you might know, Spica is selected as one of M5 mission candidates at ESA. So now JAXA and ESA are working together on that. And one nice thing is that the Spica and LiteBIRD have lots of common technologies like cryogenic system. So we are really talking to each other. And then for project point of view, most important thing is how to reduce the cost. But by having two projects pursuing the same technology, it should be a good thing. Last but not least, European LiteBIRD Consortium is a kind of a rising star. They started the first meeting in Cardiff last year in August, and then second in Paris, and third in Turin, and the fourth one was held last month in Munich. And every time it's actually growing now. We have 80 people. And ESA also started this concurrent design facility for LiteBIRD mission payload design, which is ongoing. So that's another interesting part. So I think I'm running out of time. So I guess I'm more or less, I finished all what, saying all what I wanted to say. But it's really great thing that the European Consortium is now fully active and introduces many valuable Planck lessons learned. And so I have lots more slides, but just let me provide too much detail. If you are interested, then of course I'm happy to visit that, but here's a summary. So the LiteBIRD is mission for fundamental physics with high priority in JAXA's roadmap. It's going to provide a definitive search for CMB B-mode polarization from cosmic inflation, and it's going to give insight into the quantum nature of gravity and other new physics. It's going to observe CMB polarization for 3 years at L2, and it's based on a truly international collaboration among Japan, US, Europe, Canada, and I just touch on the system overview. LiteBIRD will have two telescopes, one coming from Japan, the other coming from Europe, and the focal plane sensors are coming from US, and the readout system coming from Canada. And we are now in phase A1 for concept development, which is the most advanced state of all the other CMB polarization proposals in space. And the final selection will take place hopefully by the end of this year. And if we are selected, we will launch in mid-2020s with JAXA's A3. Okay, thank you very much.
Now, questions?
Could you explain a little bit about how do the TES bolometers work for microwaves?
Okay. The principle of TS bolometer is very simple, although I don't have that slide to explain the principle. So you have a superconductor, and then you control the temperature of the superconductor at around the critical temperature. If your superconductor is below the critical temperature, the resistance is 0, whereas above the critical temperature, you have a finite resistance. Now, by controlling your temperature around this sharp, at the sharp edge, when you have incoming light, typically CMB for instance, and CMB deposits some energy, so this superconductor behaves as sort of a bolometer, so that by having this energy deposit, the temperature goes slightly larger, and you start having finite resistance. Now, this one is coupled with the coil and some resistor. Then you can control, you can see the change of this current running on the coil. And you can pick up that difference now in the magnetic field by using squares. That's the principle. And of course, one of the keys of the success is that people invented a very nice stable feedback system. So what you actually monitor is this feedback current, in a sense. So your temperature is really kept stable. But I just explained the principle. This principle is very simple. It's a variable resistance, which is very super sensitive to the incoming light. That's a principle.
I have one that is basically coming from my complete ignorance of the inflation models.
Okay.
You showed that one of the most important measurements you are going to do is to, in this power law spectrum, be able to measure to low values of L.
Uh-huh.
And there's two components there that make up the full let's say, intensity structure.
Yeah.
One is the secondary effect, the gravitational lensing, which I think I understand because you would expect that to go down, the intensity to go down as the correlations become higher, which is towards lower end. Okay, but what drives the funny shape in the inflation model? I mean, there's a peak around 90, there's a dip around 10. What physics is driving that weird shape?
That's a very good question. Actually, this peak more or less corresponds to the size of the universe at the time of the recombination, time of the CMB generation. Okay, so it's like when you think about a fruit, the lowest wave frequency that you can create inside that is limited by the length of your instrument. Likewise, the lowest frequency of the gravitational wave, which is of course a really cosmological scale, it's really very long wavelength of the gravitational waves, but still limited by the size of the universe at the time of the CMB generation. And if you talk about the physics here, what happens is the key is scattering of CMB photons by electrons at that time. And if you have the light scattered by something, you create the polarization. Okay, so that's how the polarization itself was generated. And then if you have this gravitational waves as a background, and then space was distorted, as a result, you could create this curve pattern. But that's still, the pattern, the size of the pattern was still bound by the size of the universe at that time. Going beyond that, you cannot create any lower, vibration or sound than the beyond the length of your instrument, music instrument, like this. Whereas this one has a much